So, this is the second part of lesson 2, which unfortunately I couldn't do as part of the other lesson because I ran out of time and space for it. And here we're going to be doing the steam power station examples as well as the tutorial that we have on our textbook for the steam power station. Thank you. So, we have an example here we were asked to calculate the calorific value of the fuel that we have in this one power station. So they say that the overall efficiency at the station is 20% and that 0.6 kg of fuel is being burnt per kilowatt hour of electricity that we get out of the station. So the calorific value, we're going to put a sign of CV for it. And then we say that the heat produced will then be the kgs of coal utilized by the calorific value of the fuel. So we know that the heat equivalent of 1 kilowatt hour is actually the same as 3.6 megajoules. And the heat equivalent of 1 kilowatt hour can also be known as the 860 kilocalories. Now, your overall efficiency would be the electrical output in heat units over the heat of combustion. Or we can simply say that your overall efficiency, which is the 20%, and that is 0.2, would be equal to the overall output in heat energy, that is the 3,600 kilojoules, and we divide by your heat of combustion, which is basically that 0.6 kg times our calorific value. And therefore you can now be able to deduce what your calorific value is going to be, and in kilojoules per kilogram it becomes 30,000 kilojoules per kilogram just by using that formula, or you could have been transferring it into kilocalories. And if you do that, transferring it to kilocalories, because remember, your fuel or your coal in this case, the heat energy is in kilocalories. So therefore, we know that your 1 kilowatt hour is 860, and then you use that 860 and you divide by the 0.2, and then you would then be able to get what your CV value is, and that would simply be your 7166.67 kilocalories per joule. So your 30,000 kilojoules per kg as well as your 7166.67 kilocalories per kg would be exactly the same thing. The second example that they have is where they have a thermal station that has the following data. So here you've got a maximum demand that is 20,000 kilowatts. You have a load factor, which is 40%. Then you've got a boiler efficiency that is 85% and a turbine efficiency at 90%. The coal consumption would be at 0.9 kgs per kilowatt, and then the cost of 1 ton of coal being equal to 300 rand. So they want you to determine the following. The first one, they want the thermal efficiency of this power station. And then secondly, they want to know what would be the coal bill per annum in this station. So for the very first one where we want the thermal efficiency, the thermal efficiency would be equal to your boiler efficiency multiplied by your turbine efficiency, which is really the 0.85 multiplied by the 0.9. And then that will give us your efficiency, your thermal efficiency. Then the second one, where we're now gonna get deeper into the calculations, because we need to know what the units generated per annum are going to be. And that units generated per annum is going to be your maximum demand of the station, which was 20,000 we're given. We multiply it by the load factor of 40%, because that at the end of the day is what we get out, the 40% times your maximum demand. And then we multiply it by the number of hours that you have in a year. So to get the number of hours in a year, we know that we've got 365 days, and you multiply by 24 hours. So that will give us then the 20,000 times the 0.4 times the 876, and that will give us that value in kilowatt hour. So your coal consumption per annum, was the 0.9 kg per kilowatt hour. So we take that 0.9, we multiply it by what we've just got now, and then you divide that by 1,000. So that gives us a value in tons. So it takes it from kgs to tons. Therefore, your annual bill will be the 300 Rand of your cost of 1 ton, and then we multiply by the answer that you got in tons, and that is how much money you will be paying for coal in that particular power station a year, about 18.9 million. So the last example of this module and the last slide is we're given an example where you've got a 100 megawatt power station. And this station uses a coal with a calorific value of 26,800 kilojoules per kg. It's got a thermal efficiency of 30% and an electrical efficiency of 92%. And they want you to calculate the consumption per hour. So we start by doing the overall efficiency of our power station, and that will really be by multiplying the two efficiencies that you're given, which is the 30 and the 92%, and you get the 0.276. After that, we know that with your overall efficiency, you can have a relationship between your input power, which should be equal to your output power over that overall efficiency. So we take the power and we relate it to the energy. So instead of your input power, we say that there is a heat produced, and instead of your output power, we say it must be equal to the electrical output that you would have. And then we divide by that overall efficiency of ours. So what you would then have is you would have your output power, which is going to be that 100 megawatts. And then you need to multiply that, because you're moving from power to energy, you multiply it by your 3,600 seconds. Is your 60 minutes into your 60 seconds, because we're doing it per hour. And then you divide that entire scenario by your 0.276. And that will give you that 1304.35 times 10 to the 6 kilojoules per hour. Once you have that value, you can then say that your coal consumption per hour will simply be equal to that H divided by your calorific value. And remember, you're looking for your calorific value. So therefore, it's going to be equal to what you have worked out already. And we divide it by the 26,800 that you were given. And that is what you will have as your coal consumption per hour. And that, ladies and gentlemen, is the last part of our slide. For this module, it was very long, and I'm going to send you questions or a tutorial that you can now be able to work through at this stage. Thank you. So this is a tutorial as found in your textbooks under this chapter, and really is all about your steam generating stations. There's 6 questions in total. I'm going to do the first 3 questions with you in this lesson, and then I expect you to try and do the next 3 questions, and when we have our class, you can be able to ask, or you can even send questions via our WhatsApp group on it. So on this first question, we are now looking at a generating station which has an overall efficiency of 15% and a 0.75 kg of coal is burnt per kilowatt hour by the station. And they want us to determine the calorific value of the coal in kilocalories per kilograms. So the first thing we do, just like in the example that we had, we say that we're going to say CV is the calorific value that we're looking for, because it's just too big to write calorific value everywhere. Then we're going to say that our heat produced is equal to the mass of fuel multiplied by our CV value. So the mass of fuel have already been given as 0.75. Then you multiply by our CV value. So your heat produced is 0.75 CV. Then we know that our heat equivalent of 1 kilowatt hour, as it is said here that the coal is burned per kilowatt hour, is equal to 860 kilocalories. So your overall efficiency then becomes electrical output in heat units divided by your heat of combustion. And that basically would then give you that 0.15, which is the overall efficiency, being equal to your electrical output in heat units, which is the 860, and then it would be then divided by your heat combustion, and your heat combustion is that 0.75 multiplied by our CV value. So therefore, if you make the CV the subject of a formula, which is what I've done here, you will end up with the 7644.66 kilocalories per kg. And that's how we would go about answering this first question. Then we go to our second question. And in our second question, they say that we've got a 75 megawatt steam power station that uses coal of calorific value 64,000 kilocalories per kg. They say the thermal efficiency of the station is 30% and we've got an electrical efficiency of 80%. Then they say we must calculate the coal combustion per hour when the station is delivering its full output. So firstly, we've got to calculate our overall efficiency, which we know should be equal to our thermal efficiency multiplied by our electrical efficiency. So that's 0.3 times 0.8, and it gives us 0.24. Then the heat produced, we know, is going to be equal to our electrical output of the station divided by our overall efficiency. So if you now go into the last line that you see on the slide, that basically gives us a 75,000. Remember, it's 75,000 kilowatts. That's why it's 75,000 megawatts is the same as 75,000 kilowatts. So I multiply that by the 860, and then I divide that by my overall efficiency. And that gives me this 268.75 kilocalories times 10 to the 6 kilocalories. Then I move on to the next step where I'm now calculating coal combustion over per hour, and that is equal to my heat produced over my CV, which is my calorific value. Therefore, I take the answer that I had for my heat produced and I divide that simply by the 6,400 that I was given kilocalories per kg, and that gives me 41,992 kgs, which I can divide by 1,000 to get it into tons. As you can see, my answer is the same as the answer that is on the answer book. So in this last example that I'm going to do with you, but remember there are still 3 others that you must do on this tutorial by yourselves. I will have the 65,000 kilowatts steam power station that uses a coal calorific value of 15,000 kilocalories per kg. And if my coal consumption per kilowatt is 0.5 kg and my load factor is 40%, they want us to calculate first your overall efficiency and then your coal consumption per day. So the first formula I have is my overall efficiency, which is the same as my electrical output in heat units divided by my heat of combustion. Now for your heat of combustion, it basically equals to that calorific value of 15,000 multiplied by the 0.5 kg multiplied by the 0.4 of your load factor that your power station actually has. That will what will make you heat of combustion. So when I go into the next line already, I've now swapped around my formula so that I take the end overall and I make it into the subject of the formula so that I can end up with the 360 over my 0.5 times 0.4 times the 15,000, and that will give me my 28.67%. Then the next step is my heat produced is equal to my electrical output over my overall efficiency. Now for my heat produced, I know it should be my electrical output in heat units over that efficiency, and that simply is the 65,000, luckily it's already in kilowatts, multiplied by the 24, and then I multiply again. 24 is the day. Remember, all of these things were per hour, but we know that in a day there's 24 hours. Then I multiply it by my 860, which is my my coal per hour that I have the value. Then I divide by my overall efficiency that I just calculated, and that gives me this big value in kilocalories. Then I should say then my coal consumption per hour is going to give me the H, which is just what we calculated, divided by my calorific value. And remember, my calorific value in this case we've been given is the 15,000 kilocalories per kg. So I take the value that I just received and I divide it by the 15,000, and that will give me that 311,963 kgs, which if I divide by 1,000, I get it to be equal to 312 tons. And that is it for this second part of the lesson. Thank you very much.